Da 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 dum. Hoo yeah baby. Da 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 dum.
Oh, you surprised me. Hello. I was just reading about L.H.C. Tippett and his contributions to quality. Do you know about him? It's a fantastic story. What's wrong, Sabine? You look so depressed.
I am so frustrated about these shop floor control charts. I don't understand how the standard deviation can be calculated using a factor called D2. What is D2 anyhow?
You are very smart not to blindly apply a factor from a table like a monkey. In fact, I only know the answer because I was dumb enough to ask the same question in my graduate class with Dr. Edward Schilling of RIT. He thought this would be a great research project for me. Maybe he was trying to punish me, but I thought I was a good student.
Oh no, you're not going to put me to sleep with another math lecture, are you?
Of course not. But we must go back in time almost 100 years to solve the mystery of D2. Please come with me. Hey Sabina, please wait a minute. The time machine is hidden here somewhere.
Huh, what are you talking about?
Leonard Harry Caleb Tippett was born in 1902. He studied under Carl Pearson and Ronald Fisher. He invented the random number table, and he advanced the theory of extreme values.
Wow. There's the time machine. It's so cool.
We are going back to 1925 to visit L.H.C. Tippett so he can explain D2. That is our time machine.
Yes.
Let's go.
Great.
Yeah. I got it.
What was that?
Mr. Tippett, my name is Sabine, and I would like to learn about the mystery of D2.
Oh. You mean the expected value of the range? I will be happy to discuss this. Let's go to my office where it is quieter.
Yes. Great. Yes, yes, yes. Hoo-hoo.
It all began with Professor Carl Pearson's 1902 paper. I thought there were some deficiencies.
Oh my gosh, that's so interesting. What did you do when your experiment didn't work?
I ran my experiment again, this time with 10,000 small cards numbered according to the standard normal distribution.
I need to write this down.
I selected samples of size 2 through 1000 to obtain the range and repeated the process thousands of times to validate my mathematical results.
Fascinating. It all makes sense now.
The range is easy to understand and has direct implications on our ability to detect extreme values.
Tony, wake up. We should be going back now.
Huh? What? Oh yeah, okay, let's go.
I am so happy we were able to see LHC Tippett. He was a remarkable person and gave so much to the quality profession. But his work goes mostly unrecognized.
Yes. Of course you are right.
What's wrong, Tony? You look so depressed.
I wish I could understand, but when Tippett was talking about calculating the first, second, third, and fourth moment of the distribution of ranges, I went to sleep.
I understand, but don't worry. It is very easy to understand without calculus. Tippett gave me some diagrams and I can explain it.
That would be great. I know how important D2 is to our work in quality.
Okay, here are the diagrams Tippett gave me. The idea is simple. When sampling from a standard normal distribution, the range can be expressed in standard deviations. For example, a sample of 2 will have an expected range of 1.128 standard deviations. But, as the sample size increases, the expected value of the range will also increase. For example, a sample of 5 will have an expected range of 2.326 standard deviations. These expected values of the range were later adopted as D2. So we can set up an equivalency. The average range in physical units equals the expected range in standard units. In other words, R bar equals the expected number of standard deviations. D2 is the expected number. And then with some simple algebra, we get the control chart formula. R bar divided by D2 equals the standard deviation. And there you have it.
That's it? It is so simple.
But wait, it's even better. Look at this chart. It is a plot of the first 150 D2 values. D2 also indicates our inability to detect observations in the tails of the distribution. This function is not linear and shows a dramatic diminishing return on inspection resources. 2 samples will cover roughly 1 standard deviation. 10 samples will cover roughly 3 standard deviations. But it is not until 444 samples that we cover a full 6 standard deviations. This means that we really cannot sample inspect to assure conformance to requirements.
Oh my gosh. I think this means that our parts per million defect goal is not aligned with our sampling inspection practices.
I think you are right. Perhaps we need to rethink how we are deploying our resources. Please look at this chart Tippett gave me of his work. After Tippett did his calculations, he ran an experiment where he made 10,000 small cards and numbered them with the density of the standard normal distribution. He sampled them using his newly developed random number tables. Here is a chart showing his results for taking a sample of 10 cards. He did this 5,000 times and you can see the average result is the D2 value. As a legacy, Tippett left us with D2 values for sample sizes of n equals 2 through n equals 1000. To this day, this remains the most extensive listing of D2 values known. Tippett told me that some short-sighted black belts will wonder why anyone would use D2 for samples greater than about 8, but they have lost sight of the practical application of the expected value of the range as a powerful tool.
Thank you, Sabine. In addition to L.H.C. Tippett's 1925 article published in Biometrica, there is a very interesting article recently published in the e-magazine, Quality Digest, by Anthony Chirico.
Da 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 dum, hoo yeah baby. Da 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 dum.
And left and right.